Okay, working on our review, going on down here, we're on to the string problem or standing waves problem. What we're going to do for this one is we're going to go through and first find the velocity in the string. It says right here, you must find velocity of wave in the string first. So the whole secret to this type of problem with the strings is that there's actually two ways to find velocity, right? So I can find velocity the way we can always find velocity, which is frequency times wavelength. But we can also find velocity by putting in the tension and the length of the string and the mass of the string and then square rooting all that. So both ways work. They did tell us that this string, which has a length of 1.1 meter, is just oscillating or vibrating up and down. And so L equals 1/2 of a wave is what we see. Another way to say that is wavelength equals 2L. So anytime we see an equation we have wavelength in it, we can just replace it with 2L. For example, right here will become 2L. That's only as long as we're talking about the fundamental, but they were pretty specific about, you know, what tension must the spring be under for the fundamental. So we know it's 1.1, so we can just say 2.2 times 131. That was given. And all of a sudden we know what this is, the velocity. So plug that into our calculator. We got 131 times 2.2, and that gives us 288.2 for the velocity. So we can rearrange this, kind of set this up to get ft by itself. So we're going to end up with a v squared. We're going to also end up with this flipping. We're going to get m over L. So what that does for us really is it allows us to get tension by itself. So we're going to take 288.2 and we're going to square it, and then we're going to multiply by the mass of the string. Got to turn it into kilograms. Remember, kgms. Keep saying that over and over again, but some of you haven't heard the memo yet. So 9 grams is 0.009 kilograms, and then the length is 1.1. So I'm going to take my answer, square it. I'm going to multiply by the mass, and I'm going to divide by the length. And so the tension is 679 newtons, which is a lot of newtons, more than we could pull on our tops, right? You guys are only able to pull like 50 newtons, but you can get a string pretty tight. So if you have a string and you want it, and it happens to be 1.1 meters long, and you want it to give you a frequency of 131, you have to turn the tension to 679. Okay, so we'll fill that in, 679.6. And then we're ready to kind of take a look at the next part, which is the first three harmonics. We already kind of drew a picture of the string doing this, but I'll just redraw it. So we got our nodes and our antinodes. Here we want to put in additional antinodes. So we get something that looks like this. In the third harmonic, we're going to do something similar here. Put in another one though. So we have a total of 4 nodes and 3 antinodes. We can go through and find the wavelengths, but there's really no need. All we have to do is take the frequencies and multiply them. Since this is the second harmonic and the third harmonic, it tells us what to do. We just take that fundamental 131 and multiply by 2, and 131 and we multiply by 3. So we get 262 and 393. And that's the string problem.